Good morning, everybody. It is Monday, March 30th, and this is day one of I can determine if a treatment is effective by seeing if its mean difference is outside the confidence interval. So we talked last class about a controlled experiment. We had to randomly select a sample, then randomly assign half to a treatment group and half to a control group. We then administer the treatment to the treatment group, and we give the control group a placebo if possible. Then we analyze the data. Well, today we're going to learn how to analyze the data to see if the treatment was effective, to see if the treatment works. I find this one of the most interesting lessons out of all three Regents courses because I just find it very interesting. I feel like it's very real life applicable. This is how we see if something did its job. So we're going to kind of do this first example here. It's going to be long. We're going to spend a lot of time on it just so you understand all the components of what you're doing, but you're not going to do all of this every time you're doing a question. I'm kind of developing it here for you. So we've got 10 tomatoes are randomly selected to test the effectiveness of a treatment. From these 10 tomatoes, 5 are randomly assigned to the treatment group. Let me just get my pen going here. Let's go purple. I like purple. So this is my treatment group. They were randomly assigned. Keep that in mind. It's not like I picked the 5 biggest ones and I put them in one group. I just randomly picked them. And the other ones were put into the control group. The treatment group was administered a treatment while the control group was not. After time passed, the weights of the tomatoes were recorded. The weights are displayed. The first step in determining if a treatment is effective. Let's write these notes up here. To determine if a treatment is effective. Step 1 is to calculate the mean difference. That's going to be the treatment mean minus the control mean. So let's just kind of take it one step at a time. So to find the average of these numbers, I'm going to pull up my calculator and I'm going to add them together. So we have 9.1 plus 8.4 plus 8.0 plus 7.3 plus 5.9 divided by 5. To find the mean of something, I add the numbers and divide by that number. So that's 7.74. Remember, X bar is our symbol for mean. Now we're going to do the same thing for the other group. 7.7 plus 6.4 plus 5. Plus 5.2 plus 4.4 plus 3.8 divided by 5, and I get 5.5. So the question is, so now to find the mean difference, I'm going to do 7.74 minus 5.5, and that's going to be 2.24. So this is the mean difference. So what this means is that on average, the treatment group was 2.24 more than the control group. So does that mean the treatment was effective? I don't know that yet. The treatment group was bigger, but maybe just randomly by picking 5 tomatoes, I would have gotten 5 bigger ones. So to determine if the treatment is effective, now that I have the mean difference, I need to re-randomize the tomatoes and calculate the mean difference many times and create a sample distribution. Now this step you're generally not going to have to do when you're doing a problem. It's going to be done for you, but I'm going to kind of start you off and show you what this means. But again, you're not going to have to do this. It's going to generally be done for you. So I'm going to re-randomize the tomatoes. So let's just clean this up a little bit. So I'm just going to write in the corner here 2.24. I'm just going to erase the rest just so we have space. So what do I mean by re-randomize them? So I'm going to give them each a number. I'm going to give this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I'm going to randomly choose 5 of them. So the best way to randomly choose 5 of them is something on the calculator called a random number generator. So to access this, it's just a cool thing to use. I don't know if you've been shown this yet. I'm going to go to Math, PRB, option 5, random integer. Because these tomatoes are numbered 1 through 10, I'm going to put 1 through 10. And it's going to basically pick a random number between 1 and 10. So 10. Sometimes it repeats. 10, 2, 6, 5, 8. 10, 2, 6, 5, 8. 10, 2, 6, 5, 8. 10, 2, 6, 5. So, group 1, group 2. Group 1 is 2, which is 8.4, 5, which is 5.9, 6, which is 7.7, 8, which is 5.2, 10, which is 3.8, and the other group are the ones left over, 9.1, 8.0, 7.3, 6.4, 4.4. So now I'm going to find the mean of these groups. And again, this is something you're not going to have to do, but I want you to understand what's happening when it's doing it for you. All right, so now I'm going to do 8.4 plus 5.9 plus 7.7 plus 5.2 plus 3.8 6.2. Now I'll do it for the other group. 9.1 plus 8.0 plus 7.3 plus 6.4 plus 4.4 divided by 5. 7.04. So now for the mean difference, it's going to be 6.2 minus 7.04. 6.2 minus 7.04 is negative 0.84. And yes, you will get negatives if the treatment group is less than the control group. So what do I do with that negative 0.84? I'm going to put it onto a sample distribution. So what would I get? Negative 0.84. So negative 0.84 would be represented, that was great, represented by maybe like that dot right there. So what's happening here is the process that I just did, randomly selecting the 5, putting the rest here, find the average, subtracting them. So I did all that work to get this. Well, what's happening here is that's being done like 500 times. Each of these dots represents one of those procedures. So right now I did all that to get one dot. Now I'm going to do that like 500 or 1,000 more times. Now there's computer software that's doing that. You're not going to physically have to go through this procedure here, but understand that the computer software, that's what it's doing. It's randomly choosing 5, whether or not it got the treatment or not, putting the other 5 in a different group, find the means, and subtracting them. So now that I have this, I'm going to look at my mean difference. And my mean difference, again, was 2.24. So let's make this a little bit bigger. So 2.24 would fall right around there. So the question is that in the confidence interval? Now, you can kind of eyeball it, or you can do it more precisely. It didn't tell us how many simulations there were, so we can't exactly do it mathematically. But do you believe that this point right here is inside the confidence interval? I'd say the confidence interval, just by looking at it, probably is something like that. So that 2.24 is outside the confidence interval. So here's the tricky part. I'm gonna type this out so we can see it. In fact, let's put it up on this one. If your mean difference, the original mean difference, is inside the confidence interval, there is not a significant difference. The treatment was not effective. If your mean difference is outside the confidence interval, there is a significant difference. The treatment was effective. So I gotta explain this to you. I found this very confusing when I initially learned this, but then, once it makes sense, it makes sense. So I'm going to kind of use the sample distribution to refer to as I explain it. So what the confidence interval represents, what this represents, is expected values if the tomatoes were just randomly chosen and the mean difference was found. Regardless of the treatment, there's no treatment happening, doesn't matter about the treatment, I'm just taking half of them and I'm finding the mean differences. So I should expect, by just picking random tomatoes and find the mean differences, I should expect it to be here. So there's no reason to believe that the treatment did anything, being how these are all expected values for just randomly picking them. So if I just randomly pick them, again, they should be inside. So if it's outside, then I wouldn't have gotten that value randomly. So I shouldn't have gotten a value outside the confidence interval. The reason I did get a value outside the confidence interval is because the treatment made that big of a difference to give me a value I wouldn't have gotten randomly. So again, if the treatment is not effective, I will get something in the confidence interval because these are the values that I should have gotten if they were just randomly picked without any treatment. I shouldn't get a value outside. So the reason I did get a value outside the confidence interval, the reason I did get an unexpected value is because the treatment made it so much further from the rest. So because my 2.24 is outside the confidence interval, yes, the treatment was effective. So based on your data, does the treatment cause the tomatoes to grow bigger? Yes. 2.24 is outside the confidence interval. Therefore, the treatment was effective. That's what your answer should look like. This is a very similar lesson to the sample distribution lesson, the part threes that we spent a lot of time on. We're finding a value and we're seeing if it's inside the confidence interval or not. This lesson's a little bit different because now we're finding the mean difference and you're understanding that if the mean difference is inside, it's not effective. It didn't do anything. If it did something, it will push it outside the confidence interval. Let's try another example. 72, so let's see, this is one where I have a couple of things here, so let me just clean this up a little bit. Let's put this on a separate page. All right, let's go back to purple. I like purple. 72 students are randomly divided into two equally sized study groups. Each member of the first group is to meet with a tutor after school twice a week for an hour. The second group is given an online subscription to a tutorial account. Students in both groups are given the same tests during the year. A summary of the two groups' final grades is shown below. Calculate the mean difference in the final grades, group 1 minus group 2, and explain its meaning in the context of the problem. It's telling you to do group 1 minus group 2. You need to know that x bar is mean and sx is standard deviation. That's something you should know at this point. And it says to do group 1 minus group 2. So that's 80.16 minus 83.8. I'm going to use my own calculator. It's going to be a little bit faster than me pulling up the other one every time I need to do a little calculation. 80.16 minus 83.8 is negative 3.64. So that's the mean difference. Explain its meaning in the context of the problem. I'm going to type this. It means that on average, the students in group 1 scored 3.64 points lower than the students in group 2. That's what a mean difference is. On average, that's why mean is in the title. This group scored this much higher or lower than the other group. It's lower because my mean difference is negative. So, was the treatment effective? Is negative 3.64 a significant difference? Well, in order to know that, I need to now re-randomize all the students and create a sample distribution, which it did for you. So, again, I'm just going to copy it over to this page. In fact, I can probably do this by typing. No, let's do it by writing. Purple. So, again, negative 3.64, that's not purple, is my mean difference. Use the simulation to determine if there is a significant difference in the final grade. So negative 3.64 is going to fall right around there. So this is one where I can be a little more precise. It says it was re-randomized 500 times. So this first bar here looks like it's about 6, and this next bar looks like it's about 3. So 6 plus 3 is 9 out of 500 were negative 3.64 or more extreme. So what's 9 out of 500? We can use our calculator. That's 0.018 as a percent. That's 1.8%. The confidence interval is 95%. So 95% is inside, 5% is outside. Since 1.8% is less than 5%, 1.8% is outside the confidence interval. So is there a significant difference in the final grades? Yes, because negative 3.64 is outside the confidence interval. And again, the reason for that is that 9 out of 500, or 1.8%, is less than 5%. Understand what confidence interval is. Confidence interval is the middle 95% of the data. So if it's less than 5%, it's outside the confidence interval. If it's more than 5%, it's inside the confidence interval. And that's it. Once you get it, these aren't difficult questions, but it definitely is conceptually a little tricky to understand. That's why I'm gonna keep on explaining it over and over again. But mathematically, it's simple. Conceptually, it is definitely a little bit challenging. I want to take a look at one more together, then you'll practice. Tomorrow we'll go over one or two more together, and then you'll practice and you'll quiz tomorrow on this. All right, so let's see if we can clean this up a little bit. Let's again put them on separate pages. I think that'll be a little bit easier. So let's copy and paste it. I don't know why it's not coming out purple. It's kind of bothering me. I want purple. Purple pen. Maybe this has to be purple. Come on, purple. All right, let's give this thing a try. Purple. Okay. Ava designed an experiment to determine the effect of a new energy drink on a group of 20 volunteer students. 10 students were randomly selected to form Group 1, while the remaining 10 made up Group 2. Randomly select, randomly assign. Each student in Group 1 drank one energy drink, and each student in Group 2 drank a cola drink. 10 minutes later, their times were recorded for the reading the same paragraph of a novel. The results of the experiment are shown below. So my first step is to find my mean difference. I believe it asks that in the next question. Let's just do it now. 17, never purple, minus 19.1. I'm going to use my calculator to do that. And that's negative 1.4. So the mean difference is negative 1.4. Ava thinks drinking energy drinks makes students read faster. Let's just bring that over, negative 1.4. Using information from the experimental design are the results. Explain why Ava's hypothesis may be incorrect. I don't love this question. I think it's a little vague, at least as part of the question. I mean, some students read faster without anything. That's not a very mathematical answer, but that's good enough. Some students read faster than others, regardless of what they're drinking. Using the given results, Ava randomly mixed the 20 reading times, splits them into two groups of 10, and simulates the difference of means 232 times. Ava has decided that the difference in mean reading times is not an unusual occurrence. Support her decision using the results. So it's telling you the answer, you need to justify it. So negative 1.4 is going to fall about there. So we're going to add up each of these bars. This bar looks like it's about 2. This one's about 1, 2, 3, 2, 2. I know it's getting a little messy. 5. This one here is 1, 2, 1. That is real messy. 5, 7, 9, 11, 13. It's about 18 out of 232. You don't have to be super, super, super precise, but you should. Just based on the materials that I have here teaching this from home, it's hard for me to be very neat there. But if it's off by 1 or 2, it's fine. So 18 over 232. is 0.0775, which as a percent would be about 7.75%. So the magic number is 5. If this is more than 5, it's inside the confidence interval. So this is showing here that our mean difference is inside the confidence interval because this is more than 5%. So it is not unusual because negative 1.4 is inside the confidence interval because it occurred more than 5%. I think when I did my actual answer key where I'm able to see it a little bit clearer, I'm pretty sure this number is even bigger. But again, it doesn't have to be super precise, but it really should be precise for something like this where it's more clear. I'd like to go over one more example, and then that'll be it for the day. So let me just clean this up a little bit. Let's move both of these. I guess I'm not getting purple. Let's see if I can get green. Joseph was curious to determine if a scent improves memory. A test was created where better memory is indicated by higher test scores. A controlled experiment was performed where one group was given the test on scented paper and the other group was given the test on unscented paper. The summary statistics from the experiment are given below. Calculate the difference in the means. This is literally I literally had a student get a 65 in the Regents because she got 1 point here by, subtracting the means. So that's going to be 23 minus 18, which is 5. That's a point right there. And again, x bar is the mean. Sx is your standard deviation. A simulation was conducted in which the subject scores were re-randomized into two groups 1,000 times. So that's how many simulations there are. The differences of the group means were calculated each time. The results are shown below. So again, 5 is my mean difference. Using the simulation results to determine the interval representing the middle 95%. Use the simulation results to determine the interval representing the middle 95% of the difference to the nearest hundredth. You need to know what that means. This is something from a previous lesson. If they're asking for the middle 95%, they're asking for the confidence interval. So, confidence interval is the mean plus and minus 2 standard deviations. So it's 0.03 plus 2 times 1.548. It's 0.03 minus 2 times 1.548. You can use your calculator for that. Minus 0.03 plus 2 times 1.548. Doing each of them. So this is negative 3.066 and 3.126. It says the nearest hundredth. When you do the interval, always do the smaller one first. Negative 3.07 to 3.13. Is the difference in means in Joseph's experiment statistically significant? So that means the same thing as, is there a significant difference? Well, is 5 in the confidence interval? No. Does that mean it's significant or not significant? If it's outside the confidence interval, it's significant. If it was inside the confidence interval of random simulations, then I would have gotten that randomly. Because I got this value that I wouldn't have gotten randomly, the reason I got it is because the treatment was effective. So yes, 5 is outside the confidence interval. Now, what you could have also done, you could have looked here and saw that there's only 3 that are 5 or more. So you could have done 3 over how many simulations? 1,000. 3 over 1,000 is 0.0003, which is 0.03%, which is less than 5%. So that's what we did in the other question. We kind of did it this way. Because it gave us this information, we were able to do it by actually calculating the confidence interval. Again, I know it's a little messy. It's just a little hard for me to keep this neat based on what I have to work with here. A little bit better. So, I mean, I know I wanted to spend 2 days on this. I am still going to spend 2 days on this. But your classwork / homework, I mean, we got just a few questions left. We got 5, 6, 7 left. We got 3 questions left. So it's up to you. Okay, between today and tomorrow, we're going to finish this. So if you want to move on to 5, 6, 7 now, do it. If you want to do 1, 2, 3, 4, and then do 5, 6, 7 tomorrow before you see the lesson, that's fine. Basically, I'm going to go over 5, 6, and 7 tomorrow, and then you're going to have a 1-question quiz on this. So, again, these are your notes to determine if a treatment's effective. Calculate the mean difference, which is the treatment mean minus the control mean. Then you're not going to do step 2, but step 2 is going to be done for you generally in a question. If you're actually doing the experiment, of course, you're going to have to do that. We're going to re-randomize the tomatoes or whatever the data is and calculate the mean difference many, many times, which will create a sample distribution. Then you're looking at these 2 circumstances. If it's inside, it's not significant. The treatment wasn't effective because I would have gotten that value randomly without the treatment. If it's outside the confidence interval, I shouldn't have gotten that randomly. Therefore, the reason it was outside was because the treatment was effective. It was a significant difference. So for homework, for classwork / homework, I'm going to say for next 2 days, let's say for Monday and Tuesday, we're going to finish the worksheet. It's your packet, there's multiple pages. But tomorrow I'm going to go over the rest of it, and you will have a quiz in it tomorrow. Again, any questions, hit me up on Remind or email, whatever works best for you. And again, this one is a little conceptually tricky, so you might need to listen to me a few times. Listen to me say it over and over again until it clicks. See ya.